Hi there, today I'm going to talk to you about another assumption of linear regression analysis, which is the assumption of Homoscedasticity. All right, so usually in textbooks we teach this assumption as an Heteroscedasticity test. So we're testing for the opposite of the assumption. So the assumption is the assumption of Homoscedasticity. So I'm going to do this as follows. Homoscedasticity assumption of constant variance of the residuals or error terms. So basically, we want the error terms for a good linear regression model or an acceptable linear regression model. We would want the variance, the spread. This is what variance is, the spread of the error term to be constant. However, when we want to test whether this exists or not, there is a test called a Heteroscedasticity test, which is a test of non-constant error term. Let's a little bit talk about what is an error term again, and when is it constant and when it reveals a non-constant pattern. Let's take a look at the following example. This is an example here from a data set that I've got for the number of balls sold. So this is the balls sold, the number of balls sold, and versus the price of the rice ball in a restaurant, in an Asian restaurant. So over here we have the number of balls versus the price. And as you can see, the points spread around this red linear model, which is equal to 695.87 minus 29.595 x here is the price. All right, and the price of the rice ball seems to be responsible for or could explain 50% of the variation in the number of balls of rice sold. Now let's take a look at again what is an error. What is a residual? A residual basically is the distance between the actual value and the predicted value. How do we find the predicted value? We find the predicted value y hat to be equal to 695.8 plus, actually it is minus here, minus 29.5, let's say, 0.59 price. Right? And this is actually depicted through this linear line. So basically the error term is the difference between this actual value, actual point, actual, and the predicted, which we can get as a distance, a vertical distance from the actual to the predicted to the linear line. So this is the residual. Right? You can see that on average here, the residuals here, the spread of residuals, the range of residuals. I understand that there are residuals here smaller, bigger, higher, but the spread, the variance of residuals, this variance of residuals, it is what we're talking about, is constant. So on average here, this is the spreads. You see? The distance between the actual and the predicted, which is this one, the spread, the variance. The variance here, guys, is constant, all right? So there is no big variations. So the average, the upper bound, lower bound, if you want to understand it this way for the spread, is actually a constant, almost constant, is not that much of a difference. So in this case, when the variance is constant, this depicts a very good linear regression. And this is called a homoscedasticity situation. This is a situation of homoscedasticity, if you want to understand it this way. Homoscedasticity is a very difficult word to say. And homo in English means same. means constant variation or constant variance in the error term. So this is a desirable situation. So this is what we want it to be. All right. And what happens when we are working with multiple regression analysis with multiple independent variables, not only one independent variable like price? What if we want to add to the complexion or to the complexity of the error? Because this model only explains 50% of the variation of the number of balls sold, but we want it we want to enhance it. We want to enhance its goodness of fit. So what we need to do is possibly increase the number of independent variables. So if we also study the number of soda sold and the number of beer sold, then maybe we could get a better model. So what happens is we actually ran the analysis here through the data analysis tool pack by feeding into the regression analysis here the y to be the number of balls sold over here, and the x range being the x1, x2, x3 here, the ball price, soda, and beer. And we got the output on the same sheet. And over here we got an adjusted r squared to be 0.7. So you can see that an enhancement on the percentage that this model can explain the variation in the number of balls sold. So it's a better model than the previous one. So this is when we get multiple regression, one reason to perform or run multiple regression analysis. After depicting it or looking at the goodness of fit, and we find out the model explains 78% of the variation of the quantity of balls sold, and then after looking at the error term, and over here we have the absolute error. So in the output of the model, we get the predicted balls and we get the residuals. We added here a column on the absolute errors, ABS. So this is the error term in magnitude without the direction. And then we started testing if every point here, if every residual is even within 2 standard errors, all right, so that we can find out how many of these points are actually over the total. The count of all the cells here is the total number of residuals, and the sum is only the residuals that actually in within 2 standard errors. You can see here this point is not in within 2 standard errors. We found out that 95% of the residuals lie within 2 standard errors, and this is a very good goodness of fit. All right, then we moved on to the f-test. The null hypothesis here for the f-test is there's no linearity. Always the null hypothesis is null, is 0, no existence, like a sack that is like there's nothing in it. So there's no linearity. All right, so we want in fact this model to work out hopefully, and it's a linear model. So basically our goal for this a null hypothesis, hopefully desirable thing to happen is to reject it, so that we say there is a linearity. So basically, for us to reject the null hypothesis, this value should be less than the threshold. Threshold there is 0.05, which corresponds to 95%. It's like 5%, right, guys? 0.05. This corresponds to 95% significance. So we are 95% confident that we could, in fact, reject the null hypothesis. So if it's less than 0.05%, this means we are 95% confident that we can reject the null hypothesis of that the independent variables of the model are not linear. All right, so all together, all the independent variables here are forming a linear model. So this is what we do with the threshold. If the value here, the p-value here, the significance value here is less than 0.05, we reject the null hypothesis. If it's greater, then we accept the null hypothesis. All right, after all that, let's examine here the coefficients. These coefficients are validated based on their p-value again. So the p-values here, if they are less than 0.05, this says that, okay, they are significant. So all independent variables with the p-values less than 0.05 are actually significant. but we need to add one line, as I told you guys, given that the linearity assumptions are validated. So we need now to go ahead and validate the linearity assumptions. Before we dive into the linearity assumptions, would like to for you to take a look at what are the different assumptions here. The first assumptions, or let's take a look first at the type of data that we have. So first of all, we might get or to work with different types of data or samples. The first is the cross-sectional. Cross-sectional is the same as the data that we have over here. There's no date. The data is collected across different times, not necessarily in a series, and also probably from different restaurants, branches. So this is a cross-sectional data. With the cross-sectional data, we have to test three different assumptions. The first one is the normality assumption of error term. The second is assumption of homoscedasticity. So the third assumption is multicollinearity. All right, when the data is a time series data, and this I would cover in a different video, then we would have to also test for normality assumption of the error term, homoscedasticity, or the test of heteroscedasticity, that the error is not non-constant, multicollinearity again, but also there is another test for autocorrelation. All right. So for our case here, for this case study, we're gonna just work on with normal assumption, normality assumption, and the homoscedasticity, as well as multicollinearity. Let's go ahead with the linearity assumption. With the linearity assumption, we take the error term with its positives and negatives with as is over here, the residuals, with its positives, with its negatives, not the absolute residuals, but the residuals, and we find out the skewness and the kurtosis. So the skewness and the kurtosis over here, we need to actually benchmark it against a range, an upper bound and lower bound of the kurtosis and skewness of the normally distributed samples. So for a data set that is higher than 100 observations, so this is the sample size, higher than 100, these are the upper and 100 or higher, this is the upper and lower bounds of kurtosis and the skewness. So over here we can find that the skewness value is within the range, as well as the kurtosis value, it's within the range. Then there is no reason for us to doubt the normality assumption of residuals. So the residuals are all normally distributed. Also, along with this investigation, we can also depict it visually. So over here, we can take a look at the different residuals distributions. I'm going to do it for one of them. For example, over here, I can just format the axes in such a way that it starts with 40, so we can see the distribution way much better. So over here, I can see that there is no pattern. It is totally, completely random. The same applies here for the soda. Let me just do it one more time to show you that over here, I'm gonna start with 250 on the axes rather than 0, so that we can see the distribution way much better. And as you can see here, the distribution is totally random. There is no pattern. It's not going up. It is not curving in such a way that it is indicating a quadratic relationship or anything. It's totally random. And also we prove that with the skewness and kurtosis test. Now the second assumption, guys, is the assumption of homoscedasticity assumption. Homoscedasticity assumption is that we're assuming that the variance of the error term is constant. What does that mean? And what is the heteroskedasticity? All right, let me go ahead and explain first and foremost the difference between homo and hetero. And let me just move into our notes. So homoscedasticity assumption of constant variance of residuals is also not to be misunderstood of the heteroskedasticity test. Heteroskedasticity is a test. Homoscedasticity is an assumption. All right, what does that mean? This means the desirable situation, desirable, we're happy with Homoscedasticity. We're not happy when it is hetero. What does homo means? Homo means it is same. Hetero means it is different. You can understand it this way simply, in a simple language. Also, you can understand homo as a constant variance, and hetero as a non-constant variance. All right? What does that mean? All right. Let's take a look at our example from the Excel sheet very quickly. Over here, as a reminder, when I was talking about the spread of errors, over here, here's the error, over here, here's the error, over here is the error, over here is the error, over here is the error. But the spread of the error across the linear line here, the spread meaning from the let's say the lower bound to the upper bound, lower bound to the upper bound here, this spread is constant, seems to be constant, isn't it? Yes. However, if we take a look at this depiction, this visual depiction over here, if we assume that this is the linear model, let's say, and this is the best goodness of it linear model, which is not, and those dotted lines is nothing but showing us the upper bound of the spread of the values. Okay, I understand that over here I am defining the spread of the residuals, while over here in this example, this is a very classic example in econometrics, which is the example of the income plotted versus the age of a population or a sample of the population. So even though over here the Homoscedasticity is the assumption of constant variance of residuals. Residuals is nothing but the distance between the actual points A and the predicted point. So it's the difference between the actual point and the predicted point. It's a distance, right? So basically, if this is a linear line and the linear line here is equal y equal ax plus b, and the predicted value here is y hat ax plus b, to be precise here, then this is the actual point and this is the error, right? It's not quite straight, but it should be vertical line here, vertical, vertical, vertical. Take a look at the range here. The range here is from here to here. The range here is a bit different. Range here is a bit different. So you can see that the range actually changes. The range is not constant. The spread of the values here changes if this is the line. And over here is the same. So the range, it changes, guys, right? It's not constant. It's not beautifully spread as in here. The range upper and lower bounds. Over here, here's the upper bound of the range. Here's the upper bound. Here's the upper bound here. Here's, and you can see that there is a non-constant variance in the error term. Okay, so variance is to be understood as a spread. If you want, you can simply think of it, the spread is the range, upper and lower bound, and see how the upper and lower bounds actually changes dramatically across the linear line or the linear model or the predicted values. The linear model is nothing but the predicted values, right? So this can easily be depicted visually when we are running simple regression analysis. However, in reality over here, as I showed you, we really need a more complex model. So we ran multiple regression analysis, and we ran the multiple regression analysis with y being the number of balls and x1 the price, x2 the soda, x3 the beer. And even though we looked at different depictions or the variance of each one alone, over here I still have a little bit of a concern. We need to take a look at the residuals in totality, overall residuals, yeah? Not only the residuals per each independent variable. And for this purpose, we can't, we need to replace this price, only x1, with something that shows me x1, x2, x3, because I need to see it, the spread of all the x's. It's a multiple regression analysis. And this maybe rings a bell to you. Maybe I should write it in red, but it's okay. So this is, if we use y, predicted y value, which is beta 0, the intercept, plus beta 1, x1, beta 2, x2, and so on, then we will be able to test also the spread of the error across the different independent variables, but not, however, not with the dependent variable here. However, we would like to check it with the, what we call it, the absolute errors, with the absolute errors. So this is the test, the visual test. So we needed to plot the predicted balls sales, the predicted values of the dependent variable, and the absolute error terms, or the absolute error terms, just the magnitude of the error, the distance, the magnitude, how the magnitude, the range, the spread changes, right? The magnitude of the errors versus the predicted values. All right, let me just show you something. Now over here, maybe I should show it over here. Over here, basically, if we have the predicted values y hat with the absolute error, with the absolute errors, E, what happens is, as you can see, as the y here, the y hat, the predicted values increases, also the variance increases, also the magnitude of the errors increases. Can you see that? So basically, as this increases, the magnitude of the errors increases. So if we plot the absolute errors versus the predicted values, and we get a linear depiction that shows us that the absolute errors are dependent on the predicted value, basically as the predicted value increases, the absolute errors increases, this is a big problem. This is a heteroskedasticity situation. This is bad. This is something that we don't want. This is heteroskedasticity. And basically this is exactly what this is. You see, this is the predicted value over here, the predicted value across the x-axis. As it increases, the variance increases, the magnitude of the errors, you can see, also increases. You see that in general, and this means that there's a linear depiction here. This is really bad. This is really bad. This is heteroskedasticity. Now, if there's no heteroskedasticity, what happens is we're going to get something like this. Instead of something sharply going up, that there is a relationship as this increases the predicted value, the error term increases, or as let's say that if you want to take a look at it or you look at it in this way, also we wanted something. The desirable situation is we want something to look like this, more flat, like that. So the correlation is not very high, and there is some distortion, like it's not nicely linear regression. It's not nicely tight, like in here. It's actually more spread out. Even if there's any deformation, that's even better. This means that there is no linear depiction. This means that the absolute errors are not dependent on the predicted. Now, let's take a look at our example. In our example, what we've done is from the output, we plotted the absolute errors. So be careful. You're getting with the output, we're getting the residuals. You need to get the absolute residuals. And with the absolute residuals here, you just use the function ABS and you plot it against the predicted values. As we can see here, there is not sharp linear line, yeah, and it's a little bit more flatty. Also, if you're looking at the R squared explains that predicted values explains only 2% of the variation in the absolute error. This means that the predicted values of the balls of the rice balls does not explain much of the variation. This means that this absolute error is not dependent on the predicted values. And if you also take a look over here, there is some problems. This is the deformation that we were talking about it. So there's not much of the linear relationship here. There's not much that we can say that as the predicted values increases, the absolute error increases. Not necessarily a valid linear assumption. And one thing to say why this is a big problem with linear assumption, with linear regression is, guys, over here, this model, this linear model, the line, predicts these values, the lower values of age. The prediction here is more precise. Why? Because the error here is smaller. The spread of the error is lower. However, if we want to predict based on this linear model, we want to predict income for those who are 40 years and above, you can see that the errors here, the magnitude of the errors is huge compared to the errors of the other group of individuals. And for this reason, this linear model, the precision level across this linear model varies. It's not a very good model. So this is why it is a big no, all right? So basically, this is how we test or detect heteroskedasticity visually. However, this is a bit more advanced, but I think you can also take this example. Look at this example, guys. This example, as you can see, it looks like a bow tie. This is the bow tie example, I call it. And over here, you can see that the spread of errors is high up to a certain point, then it is constant, and then it is high. In fact, this whole model is not linear model per se. But if you get a linear model like this, for example, and for some reason you wanted to, everything went well, in this case, the spread of the errors is very deformative, and it goes as the following: high, constant, high. So it's not as this increases, it's actually as this increases, it increases, this constant, and it increases. So for this purpose, there is another test, guys, that is quite advanced, but it's not very difficult. And this test is called the Breusch-Pagan test. It's a test for heteroskedasticity. What is heteroskedasticity? Heteroskedasticity is basically this situation and this situation, that there's a non-constant variance. There is a cone like depiction of the predicted, actually not of the predicted, this is for simple regression, but for multiple regression we use the predicted and we use the absolute errors. So there's a certain relationship between them. So this is heteroskedasticity, the non-constant error term. All right. Let's take a look at this Breusch-Pagan test. With this Breusch-Pagan test is called also the chi-squared heteroskedasticity test. It's chi-squared test, and you can memorize here squared, chi-squared, so that when you want to run the first step of this test, remember all the time to square the y, the residuals, to square the residuals, and that will be the y. So basically for this test, the first step is to run linear regression, where the x, the independent variables of the linear regression, is the independent variables of the original regression, all the independent variables as you can see here, but the y is not the residuals, but the residuals squared. Okay, so it's chi-squared test, as you can see here. It's a chi-squared based test, and it takes the residuals squared. It has nothing to do with it, guys. It's just the name is chi-squared. But I just wanted you to take this as a reminder that you need to square the residuals, all right? So you don't take the residuals as is, you need to square them, and then after you square them, you go to the analysis toolpack and get the regression output. Once you get the regression output, what you need to do here is you need to perform the test, calculate the value of the test. And the value of the test is very easy. It's n, and n here is the number of observations multiplied by the r square. And r square, you can get it here from the output. So n, you can get it by using the count function, and you count all the values from beginning to end, right? So you can hold down shift control and the down arrow, sorry, and you can get the values. All right, so now let me show you how I computed this value. Basically, this is count all the way from B4 all the way down to B189 multiplied by the r squared. Now this value, I need to get the p-value. It's like a weight, a coefficient, and I need the p-value for it. For the p-value, guys, on Excel, you need to get the following function. The function is, let me show you. The function is chi-square dot distribution dot rt, and you feed into that the value that we got from the chi-squared. The m5 is basically the value that we just computed, which is n multiplied by the n square. And over here, 3 is the degree of freedom. Degree of freedom is basically the number of independent variables. Over here in our example, we have 3 different independent variables. So we have 3 independent variables. So basically we just feed into there the value and the 3 independent variables, and we got it. All right, now how do we interpret this value? This test, Breusch Pagan test, is a test for heteroskedasticity. Okay, all right, so these people are working on heteroskedasticity. So their null assumption is that there is no heteroskedasticity. All right, so this is the null assumption, the null hypothesis. The null hypothesis, no heteroskedasticity. Okay, no heteroskedasticity. Is it a good thing or a bad thing? In our case here, it's a good thing. So I really do not want to reject the null hypothesis in this case. In this case, I am happy with no heteroskedasticity. I would love to accept the null hypothesis. Usually over here with analysis with linear regression in general, when the threshold is less than 0.05, we reject the null hypothesis, right? It's very evident here on the F significance F. When it's less than 0.05, we reject the null hypothesis. So basically with this test, with the Breusch Pagan test, we want this value to be greater than 0.05 so that we don't reject the null hypothesis, we fail to reject the null hypothesis, and we accept it. And then we say that there is no heteroskedasticity. And this is what happened in this case. In this case, the p-value is 0.1 and it's greater than 0.05, which is the 95% confidence that we cannot reject the null hypothesis. We actually gonna accept the null hypothesis of no heteroskedasticity, and this is it. If there is no heteroskedasticity, then this means that this is another checklist, another item on the checklist where these p-values could be validated. All right, next is the third assumption. The third assumption, guys, for linear regression, and over here in my notes, I showed you ways on how to correct for heteroskedasticity. Basically, you can take the natural logarithm of the y of the dependent variable, or you can take the square root of the dependent variable and run the linear regression again and see if heteroskedasticity is still there. If it's not there, then good for you. You can continue to run your analysis. Over here, this was an example of heteroskedasticity, guys. Do you see the example here? We have the predicted spending and the absolute error, and you can see that the predicted spending and the absolute error has a very significant linear model over here, and predicted spending, it can explain about 32% of the variation of the absolute errors. So this is an example of heteroskedasticity. Why? Because there is a nice fine linear regression, linear line between a predicted independent variable and between the predicted value, the y hat, and the absolute errors. Okay, so now let me jump to multicollinearity, because autocorrelation is when the data is time series data. With multicollinearity, if two or more independent variables in the regression analysis are highly correlated, regression analysis may yield strange results. Whenever two or more independent variables are highly correlated and the regression coefficients won't make sense, then you will say that multicollinearity exists, and this means that there's a high correlation between the independent variables among themselves, and this will confuse the results. So let's go ahead and test for multicollinearity. There are certain ways that you can test for multicollinearity. The first one is basically to find a correlational matrix of the independent variables. So basically you can go to the data analysis tool pack and go to correlation, and then set OK and take the input being all these independent variables. Hold down Control Shift and down arrow to select all the values. Don't forget to include the labels if you did so, and put the output range somewhere around here, guys. The same Excel sheet, let's put it. So let's put it somewhere here. And here we go. So this is the correlational matrix. This correlational matrix over here shows us that the price is highly correlated to the soda, 0.2, soda and beer. So this is price and soda, price and beer. So price and beer is not highly correlated, but who knows, maybe for you this is highly correlated. Over here, soda and beer is not highly correlated, but price and soda, on the other hand, are highly correlated. You can see that. Now, some of you might say, well, maybe 0.5 is not highly correlated, maybe 0.7 is highly correlated. I agree with you. There's always room for interpretation. For this purpose, I am going to also teach you a little bit more advanced test rather than just the correlational matrix. And this advanced test is actually taking the VIF, computing the VIF value. And the VIF value is basically it could be obtained from Excel through multiple steps. Usually with SPSS, you get it easily. With our software, you get it also easily. But this variance inflation factor, the VIF, the variance inflation factor, we can get it by the following. Let me show you how we get it. I think I do. Do I have the already done test so it can save us time? Yes, I do. So over here I have it done. So this for saving us some time. I hope I have it here. Oh, unfortunately I don't. Okay, so let's do it from scratch. So with the VIF, I'm going to start with a new Excel sheet, And basically, I'm going to find the regression analysis. I'm going to do the output for the regression analysis with every independent variable being the dependent variable and the others being the independent variable at each time. So basically, each independent variable get to be the dependent variable in the regression analysis at one time, while the other independent variables will be the independent variables of the a regression model. So let's run this very quickly. Basically, you're going to go data analysis, and regression. The y is the price here, and the x is these guys. And you don't want the whole output, you just need the r square, and not the adjusted, but the r square. So this is the value that you're looking for, the r square. All right. Okay, so let's do the same here. In this case, beer will be the y. So over here, the y range will be beer, the one in red, while the independent variables will be the remaining independent variables. Let's set the output range to be somewhere close. And what you need really is the r square, this value. Same applies over here. I rearrange the order so that we can run it smoothly. So the y will be the soda, while the x will be the other remaining independent variables. It doesn't take that long, but it requires a lot of patience, especially if you have many independent variables. Okay, so now what I need to do is I'm going to go back to this and compute the variance inflation factor, the VIF. So I'm going to compute that with the following equation. It's 1 over 1 minus r squared, which is 1 minus this value. For the first one is the bowl of price, the price of the bowl of rice. And here it is. So did you see what I did over here? Basically, it is 1, the VIF formula is 1 over 1 minus r squared. Okay, 1 over 1 minus the r squared when the independent variable was the dependent variable here for the VIF computation. So the next value will be the VIF for soda. So be careful with the arrangements here. It's going to be 1 over 1 minus, and it's when soda was the dependent variable. Oh. And over here is 1, again over 1 minus, when the dependent variable was beer. So 1 minus when the dependent variable was beer. So now you understand why I highlighted it in red, so that I myself won't get confused. So over here, these are the VIF values. As you can see, the VIF values are below 5. When the VIF values are below 5, then we can say that there is no evidence of multicollinearity. When the values range between 5 and 10, then we have a strong reason to doubt the presence of multicollinearity. So this is how we interpret. A value of 1 indicates there is no correlation. So a value of 1 indicates there is no correlation between this given explanatory variable and any other variables in the model. Okay? Now, what happens with a value between 1 and 5? Values between 1 and 5 indicates moderate correlations. It's moderate correlational or moderate correlation between a given explanatory or predictable variable and other explanatory variables in the model. But what do we do then? But this is often not severe enough to require attention. Now, when the values are greater than 5, what happens is this indicates potentially severe correlation between a given explanatory variable and other explanatory variables. Of course, the given explanatory variable is the one that was dependent variable in the model, and other explanatory variables in the model. And what do we do then? In this case, the coefficient estimates and the p-values in the original regression output are likely unreliable. Are likely unreliable. So please be careful. In our case over here, we got a VIF of 1, which indicates no correlation. So even though I highlighted 0.5 as a high correlation, but it's not high enough to indicate a problem. And in this case, we validated the 3 major assumptions for this linear model, and this linear model, which is which model? Which is this model. Number of balls will be equal to, or the estimated number of balls, the predicted number of balls will be equal to the intercept, which is 333.47. Let's say take only 2 decimal points multiplied by price. I'm going to just put price for now, plus 0.59 soda plus 0.21 beer. Now we are ready to interpret the coefficients of this model. After we validate all the assumptions, let's do the coefficient interpretation of this model. No. Oh, I missed it. Did I miss it? No, I didn't. Good. Here's copy. And here's paste. So what does that mean? This means that when the values of all the independent variables are 0, when the price is 0, soda is 0, number of whatever is 0, then the this model is really difficult to interpret the intercept. So I'm going to just skip this interpretation of the intercept. So let's just say that the if the price is constant, that there's no change in price, no change in no soda, no beer, then the number of balls sold will be 333. Okay. What happens now with the price? How do we interpret the coefficient of the price? With the coefficient of the price, we say as the price of a rice ball or of the ball increases by $1, let's use the natural English language, not say by 1 unit. Yeah, I understand. This is the standard template. As the independent variable increases by 1 unit, the dependent variable either increases or decreases based on the sign of the coefficient by that amount, right? But with the natural language, to show that we deeply understand what this model is about, this is how we interpret it. As the price of ball increases by $1, what happens? The number of rice balls sold decreases by an average, or by about, or by an estimate, by an average. If you say an average is not a mistake, it's okay. It's all the linear model is nothing but an average, the mean, by an average of 13, let's say 13 balls. Some might say you can say 14 because it is over 0.5, because it's 13.9, but you can just an average, you're saying, right? So it's okay. This is why we add the word average, right? By an average of 13 balls. So if you increase your price for each ball by $1, you will sell 13 balls less. But at the same time, on each ball, you will make more money, right? So you need to see how you would like to price your products. All right, how about the soda? As the number of soda cans sold increases by 1, the number of rice balls sold increases by 0.5 or 0.6 balls. But this is why we need an average. Increases by an average of. You see why we need the average? The same applies here for the beer. As the number of beer cans sold increases by 1, the number of rice balls sold increases by an average of 0.21. And this is it. This is how we run linear regression analysis and its assumptions. Basically, if any of these assumptions, I say basically a lot, so any of these assumptions are invalidated, if we find out VIF here is 9 or if it's 8, then we have a reason to doubt multicollinearity. What happens is that all this model collapses. Even all these p-values that we found here being less than 0.05, and we're saying that all the independent variables are significant, but remember, they are significant only if the linearity assumptions hold true, hold valid. If you fail to validate all these assumptions, then these coefficients, these p-values here are invalid. They mean nothing. This is not necessarily a reality. It's not necessarily true. It's not necessarily valid or reliable. All right. So guys, I hope this video is helpful. Thank you so much, and I'll see you in class.